Hi everyone. Here we introduce stochastic financial modeling in continuous time. This lesson is mainly concerned with the technicalities. We consider the model setup, where we have multiple assets, each driven by a semi-martingale, typically an ether diffusion. We look at the notion of a numeraire. We introduce the self-financing condition for portfolios. We'll have a look at martingale valuation and the construction of an equivalent martingale measure using the Kirsanov's theorem and the market price of risk. And finally, we will have a look at hedging and its relationship to the martingale representation theorem, and also have a brief look at the so-called Malevin calculus. Basically, we will extend all the results that we obtained in the discrete time cases for the single period and the multi-period models to the continuous time case. So let's have a look at the general setup. We will be dealing with market models, and each of these models is a tuple of the following form. It consists of a probability space, omega fp, a filtration ft, assumed to satisfy the usual conditions, as well as a tuple of asset price processes, and this is going to be an capital N plus one dimensional adapted Cadillac semi-martingale. Right now, each of these SIs is best thought of as a stock price process, and S0 will play the role of the bank account, as we shall see. Now recall that the work of Delban and Schakemeyer has shown that for a securities market model to be arbitrage-free, it is necessary that the underlying assets are semi-martingales. That's not to say that non-semi-martingales are not used in financial modeling. Fractional Brownian motion, for example, is not a semi-martingale and is used in rough volatility modeling. There the underlying asset is still a semi-martingale, although the volatility process is not. As far as I know, the semi-martingale requirement can also be weakened if you introduce transaction costs. In any case, we will typically assume a finite time horizon from 0 to capital T, and we will also make the usual unrealistic assumptions about the market, in other words, frictionless markets, no transaction costs, taxes, completely liquid markets where assets can be traded in any desired amount and short sales are permitted. We assume no default risk, and we will also assume that there are no arbitrage opportunities. In short, we assume the kind of photoshopped version of reality that mathematicians typically like to work in. In this course, we will specialize to a Brownian world. We will assume that omega, the sample space, comes equipped with a k-dimensional Brownian motion, W, which consists of components W1 up to Wk, and that Brownian motion generates the filtration Ft, augmented to satisfy the usual conditions. In that case, we say that we have k sources of noise. The asset price process, which is multidimensional here, is given by an ether diffusion of the following form. And this is a multidimensional stochastic differential equation, which is an abbreviation for this expression shown here. Notice that the volatility matrix is an n plus 1 by k matrix. As I've mentioned already, S0 will play the role of the riskless bank account. I've put riskless in inverted commas here because the risk that is excluded is default risk. There's definitely interest rate risk, and we will see how to model interest rates later on in this course. The bank account is assumed to have the following dynamics, where R here is the short rate, which may be stochastic. As you can see, there is no volatility component for the bank account. We will also assume that the bank account process starts at 1. So if at time 0 you have, say, 10 Rand in the bank, that is equivalent to owning 10 bank accounts. A numeraire is a price process NT of a non-dividend paying asset with the property that NT is strictly greater than 0 almost surely over the period from 0 to capital T. You can think of a numeraire as a unit into which other assets are translated. For example, if ST is the price of S in money, in rands or in dollars, then S hat T, defined to be ST divided by NT, is the price of S in units of N. For example, if a barrel of oil costs $50 and a loaf of bread costs $2, then the price of a loaf of bread in barrels of oil is 2 divided by 50, in other words 0.04. The restriction that N be the price process of a non-dividend paying asset isn't particularly strong. If an asset does pay dividends, then the associated numeraire will be the portfolio consisting of that asset with all the dividends reinvested in that asset. In other words, the moment the asset pays any dividends, those dividends are used to buy more of the assets, which are then put into that portfolio. Initially, as in discrete time, we will use the money market account or bank account S0 as the numeraire, and we will write S bar T to be the discounted value of S. In other words, S divided by the value of the bank accounts. That's then the value of S in terms of the numeraire. Very soon, however, we will be using different assets as numeraire. Changes of numeraire and measure are a very powerful method for simplifying certain problems. Next, we define European-style contingent claims. A European-style claim, C, with maturity capital T, is simply an FT measurable random variable, which we will interpret as a payoff at time capital T. To begin with, a trading strategy or portfolio is just a predictable process, phi t, which has as many components as there are assets, and which is integrable with respect to the semi-martingale st. Here phi nt is to be thought of as the number of units of asset Sn held in the portfolio at time t. The value and gains processes associated with the portfolio phi are then defined as follows. The value process Vt phi, in other words the value of the portfolio phi at time t, is simply the dot product of the vector phi t with the vector st. In other words, it's the number of shares times the price per share summed over all shares. We can then define the gains process Gt phi, which is the gain on the portfolio phi by time t, as the value at time t minus the value at time 0. Observe that the differential of V and G are the same. This is because V0 phi is a known constant and it does not depend on t. Given a numeraire process n, the numeraire deflated or numeraire discounted value and gains processes are defined similarly. V hat phi is defined to be V divided by n, in other words discounted or deflated by n. And G hat T of phi is V hat T of phi minus V hat 0 phi. Observe that G hat T of phi is not the same as GT of phi divided by NT in general. That's because if we look at this expression here, in the first term we are dividing by n at time t, but in the second term we're dividing by n at time 0. We now introduce the notion of a self-financing portfolio in continuous time. A trading strategy phi is said to be self-financing if and only if the Vt is equal to phi dst. In other words, if and only if the value of phi at time t is the initial value plus the stochastic integral from 0 to t of the portfolio phi u with respect to the asset price process Su. Remember here S is multidimensional, so this is a dot product. Equivalently, the gains process is simply the stochastic integral. Because phi and S are vectors here, and this is a dot product, this amounts to saying that the gain on the portfolio phi is equal to the sum of the gains on the individual components of the portfolio using the appropriate stock price. What this means is that the instantaneous change in the value of the portfolio is due to the changes in the asset prices and not due to the changes in the composition of the portfolio. As I've mentioned before, dV is equal to dG, and by the definition of self-financing, both are equal to phi dot dst. Now typically, we will require even stronger conditions on portfolios. For example, a self-financing trading strategy is called admissible if its value is non-negative almost surely for all t. Conditions like this are necessary to prevent arbitrage in the models, for example via doubling strategies, where arbitrarily large losses can be sustained until an eventual win. In an exercise, you will see how to construct a arbitrage like that in the Black-Scholes model. But that arbitrage is not admissible. Now, the self-financing condition, as we have just stated it for continuous time, looks rather different to the condition that we had in discrete time, so we want to provide a little bit of intuition for it. Begin by discretizing time, and suppose that phi t is the portfolio held over a period from t to t plus delta t. In other words, phi t is constant over this period. In discrete time, if you recall, the self-financing condition is given as follows. Phi t minus delta t dot st is equal to phi t dot st. You can think of the left-hand side as the value of the old portfolio at time t, and the right-hand side as the value of the new portfolio at time t, where the portfolio is rebalanced at time t. If we rearrange this expression, we obtain the following. And that looks like st times the change in phi is equal to 0. In the limit, as we let delta t go to 0, this suggests that we obtain the following expression. St dot d phi t is equal to 0. However, it would be wrong to use this as the self-financing condition for the following reasons. Firstly, stochastic integrals are to be interpreted in the Ito sense. If ht is a left continuous adaptive process, then the stochastic integral from 0 to t of ht with respect to a semi-martingale xt is the limit over ever finite partitions of the following sum. And what we see here is that the terms look like terms in a left-hand Riemann-Stieltje sum, where the integrand is known at the initial time of the interval. If we look at this expression over here, however, the integrand is st and it is known at the terminal time. In other words, it looks like a term in a right-hand Riemann-Stieltje sum. So we have to interpret this result that we obtained from discrete time somehow in the Ito sense using left-hand Riemann-Stieltje sums. In order to do that, we rearrange it to obtain the following expression, as you can verify yourself simply by multiplying out. Now, as you can see, in this case, the integrand is known at the initial time. So this term here can be interpreted as a left-hand Riemann-Stieltje sum. And over here, we have a product of two differences, and that can be interpreted as a term in the covariation between s and phi. In other words, in the limit as delta t goes to 0, we obtain the following. St times d phi t plus the differential of the covariation between s and phi is equal to 0. That's because the first term is a left-hand sum and therefore can be interpreted as a stochastic integral in the Ito sense, and the second term looks like a summand in the covariation process. Now, by Ito's formula, in particular the product form, if we look at the differential of V, the portfolio value process, that's the differential of phi dot s, and that can be written as phi times ds plus s times d phi plus the differential of the covariation of s with phi. If we look at the last two terms, we see that they are 0. In other words, we just obtained the first term, and that's a self-financing condition we've defined. I have to stress here that this argument is purely intuitive. Trading strategies must be predictable, but need not be semi-martingales, and terms like st d phi t and d square brackets s phi need not make sense. As in discrete time, we say that a European-style contingent claim C with maturity capital T is attainable if and only if there exists a self-financing strategy phi with the property that the value of the claim at the terminal time t, in other words the payoff, is equal to the value of the portfolio at that time. In that case, phi is called the replicating portfolio for the claim C. We also say that a securities market model is complete if and only if every contingent claim is attainable. In other words, if and only if for every ft measurable random variable we can find such a portfolio. Here is a useful proposition. A self-financing portfolio remains self-financing under a change of numeraire. By this is meant the following. If the portfolio is self-financing as we've defined it, in other words, if dV is equal to dG is equal to phi ds, and if n is a numeraire, then d hat v is equal to d hat g is equal to phi d hat s. Here v hat, g hat, and s hat are the numeraire deflated value process, gains process, and stock price processes, respectively. Before we prove the result, recall the following facts from stochastic calculus. Square brackets h bullet xy is equal to h bullet square brackets xy. And thus the differentials satisfy the following relation here. In particular, if we look at the differential of the covariation of the value process with 1 over the numeraire, then the value process is given as follows by the self-financing condition. Of course, V0 isn't changing, and so that just leaves us with this result here, which by the line above simplifies to the following. Let's now proceed with the proof. Recall that V hat is V over N. So D of V hat is equal to D V over N, which by the Ito formula in the product form is 1 over N times dV plus V times D 1 over N plus the differential of the covariation of V with 1 over N. Now by the self-financing condition, dV is phi ds. By definition of value process, V is just equal to phi dot s. And by what we've just seen, the differential of square brackets V 1 over N is phi times the differential of S with 1 over N. What we see in this case is that each term has a common factor of phi, which we can take outside. Then if we look at the expression in parentheses over here, it takes exactly the same form as the first line, except that V has now become replaced by S. Since the top line is dV hat, the expression in parentheses must be ds hat. And thus dV hat is equal to phi ds hat, which is what we had to prove. In particular, if phi is self-financing, then using the bank account as numeraire, we see that the differential of the discounted value of the portfolio is phi times the differential of the discounted share prices. As an immediate corollary, we obtain the following result. If a contingent claim is attainable in a given numeraire, it is also attainable in any other numeraire, and the replicating portfolio is the same. In other words, if x can be represented as v0 plus the stochastic integral from 0 to capital T of phi with respect to s, then x hat is equal to v0 hat plus the stochastic integral of phi with respect to s hat. Now, as in discrete time, a self-financing portfolio phi with n plus 1 components is completely determined by its initial value and n of the n plus 1 components. For example, if we take S0 to be the numeraire and we suppose that we're given the initial value V0 as well as the risky asset components of the portfolio phi 1 up to phi n, then the value of the riskless asset component phi 0 is completely determined by the self-financing condition. In fact, by the self-financing condition, V bar at time t is equal to V bar at time 0 plus the sum of the stochastic integrals, where we are summing over all the assets. However, S bar 0, in other words the discounted bank account, isn't changing, so ds bar 0 is 0, and hence the bank account does not contribute to the discounted gain. In other words, what we obtain is this sum here, where now we're summing only over the risky assets. We can use this expression now to solve for the bank account component of the portfolio. This result is actually very useful. It means that we often don't need to worry about the self-financing condition. What we do is we work with discounted or numeraire deflated asset processes. We work out the components of the portfolio phi for the risky assets. And then we simply say choose phi 0 to make the portfolio self-financing with a given desirable initial value. In other words, we can impose the self-financing condition afterwards, and we do not have to worry about it at the beginning.